We are live now.
Ok, bueno, puedo dar la bienvenida en español, ¿no? Bienvenidos a todos al tercer día. Welcome back to the last day of this summer school. We have great talks today, so I will pass them to Tamar to introduce the speaker from today.
All right. Welcome, good morning, good afternoon, good evening, everyone, depending on your side of the world. It's morning for me. I'm delighted to introduce today's speaker, Professor Heng Ji. She's professor in computer science in the computer science department at the University of Urbana, Illinois. Okay, let me get the professor in computer science in the computer science department and affiliated faculty member in electrical and computing engineering at the University of Illinois in Urbana-Champaign. Heng Ji is another super successful speaker that we're very lucky to have today. So her research interests are in multimedia, multilingual information extraction, knowledge-based population, and knowledge-driven generation. And she has a very long list of awards and recognitions. I'm going to just mention a couple. So she was awarded the AI Stand to Watch by the IEEE Intelligent Systems in 2013. She's recipient of the NSF Career Award in 2009, recipient of several Google Research Awards and the IBM Watson Faculty Award in 2012 and 2014. And more recently, she is currently elected secretary to the North American chapter of the Association of Computational Linguistics, and she has received multiple funding from different federal government agencies like DARPA, ARL, IARPA, NSF, and DHS. And so with that, please join me in welcome Professor Heng Ji, and Heng, take it away.
Thank you so much, Kama. Good morning, everyone. I really wish I could be in Mexico with all of you. I hope I can join some nice trip later, maybe after a couple of years when we do the NACO conference in Mexico. Today I would like to talk about a very recent research thread that I have been pursuing. And a lot of the work I will be presenting is still ongoing and quite preliminary. So I would like to welcome any feedback, and please feel free to interrupt me if you have any questions or comments. And I will have a couple of quiz, try to make the presentation more interactive. Okay, so the title is about how to write a history book. This is based on my collaboration with Professor Shiv Chang at Columbia University and Professor Kyung Cho from NYU. And it's done by many of my amazing students. And I will talk about their names when I present each work. So the motivation is because we are facing a information pollution era, which means we are seeing a lot of misinformation and disinformation on the web, on the news media, social media. And this problem is not new because it was old problem. It has always been there, and we were just not so aware of that problem in the past compared to right now. So for example, in the older days, many years ago in World War II, Japanese troops, they invaded to many cities in China. They killed many people. So there's a very big massacre in Nanjing. If you look at the history book in Japanese schools, there's very little about this event, and they don't talk about the details. And in their social media, they often say it's impossible to have 300,000 people died because it's impossible for the city to hold so many dead bodies, for example. So they try to give evidence, and young people don't trust this number. And so this is not okay because it's international human right to know what happened in history, but it's not kind of affecting our daily life, right? So we can debate about it, we can argue about it, but it's not a really, life and die issue for us. However, in the current days, we still have this information pollution problem. So, for example, we are still trying to figure out what happened in the pandemic, right? What is the origin of the coronavirus? So one piece of misinformation is about this woman soldier, U.S. Army. She attended a event, a sports event in Wuhan that was in October 2019. And then she came back to US, but she was never tested positive. So she never got coronavirus. But somehow, based on this connected network, many people actually believe this misinformation. I mean, in different regions, and they kind of connect the dots, and they kind of biased by the information they receive, and they tend to trust some rumors and some misinformation in some certain way. So the question we want to answer is why people believe this kind of misinformation. What happened in this construction of the misinformation so that it's so convincing that people will be misled by this network, for example. So if you look at this graph, everything is kind of coherent except the fact that she was never tested positive. So that means when we are looking at information graph, it will be really important to figure out which piece of information, which nodes and which edges, which path is accurate and coherent before we draw our conclusion. Because humans are really good at connecting dots, so maybe we should let the machine do the verification as well. So before I start talk about the solution, I would like to kind of show the horizon of this problem. Like it's really big and it's really serious, and it's very hard for human to detect misinformation. So I would like to show a couple of examples. So this one, you can see two articles for the same image and caption. And I would like to ask the audience to maybe, let me see what I can do, vote. I cannot. So if people can post your reply or just speak up if you can, which one do you think is a fake news? So the difference is highlighted in red color. So these parts are different compared to the left one. Try to see how I can do this. Is it possible people can post messages or speak up? I don't know how this format works.
So yes, they can raise their hand if they want to make a guess, or they can post on the chat. They can post also on the Q&A if they want, and okay. We can give them audio too.
Yeah. So let me see. Okay, so I can see chat. Does anyone want to say which one is fake? It's quite hard to read because it's event that's happening in another foreign country that you probably don't pay attention to about the current news. Left is fake. Yeah, so some people said it's hard to tell. Yeah, it's very hard. I was not able to tell which one. Yeah, so actually the right one is fake. The reason is because this organization is not funded by this organization. And this person did not say this statement. I mean, he did not make this statement. But if you are not keeping checking of the, what's going on in this country, it's almost impossible to figure out this kind of a misinformation. And let me try to show a maybe simpler example. This one is only for the caption. So from this image, the left one and the right one, they are both talking about these soldiers. They left. They are in a place, but the left one says they are leaving. The right one says they just arrived at this facility. So I guess if we want to figure out which one is we have to look at the scene of this park, and probably we should, if we visit this place, we can know which one is the entrance, right? But otherwise, it's just impossible. Maybe we can look at their the way they live. They are happy or they're sad, and then we try to figure out which one's fake. Does anyone want to make another guess? Which one do you think is it's fake? Okay, I'm checking my chat. Left one. So some people said the left one is fake. Okay, actually many people said the left one is fake. One person said it's on. Oh, okay, actually half. Okay, so yeah, so the fake one is left one. So many of you guessed right. So they just arrived. Maybe because you can see, I don't know, it's hard to tell. The way they carry things, or just looks like this is coming inside the facility. Okay, so one more. So this one shows a train station, and there's some logo here, and there's some street scenes look quite special. So we probably can tell this must be in Europe, right? Because it looks like a building in Europe. But the left one says it's in Milan. The right one says it's in downtown Berlin. Although it also mentions something about Milan. I guess this one is easier to guess which one is fake. Right one, yeah. So now everyone agree, most people agree the right one is fake. Yeah, so this one is easier to detect because it's talking about two cities without much connection, and the scene does look like Milan, right? Like old streets, and if you can understand this phrase, maybe you know this is from Milan. Anyway, so the point is that current information ingestion techniques are not sufficient to solve this problem, because we usually just look at entity-centric knowledge base, which means you look at an entity and another entity, whether they have any relations and what kind of activities an entity is involved, but we care much less on events, right? So if you ask anyone in US who is Barack Obama's wife, I think most of them can give an accurate answer. But if you ask any journalist or any historian, what is the list of the list of people who died from COVID-19 from the whole world, or even from a city, and who are they? No one can give an accurate list within short time, right? So in other situations, we will have to gather the information from multiple sources and then do verification. So for example, if you look at the mainland news and the Hong Kong local news about what happened in Hong Kong 2019 protest, even though they give you exactly the same source, the same pictures, but they will give you a very different narrative. So sometimes they say the attacker is police. In other sources, they may say the attacker are the protesters. So the goal of this work is to be able to generate a authentic summary about what happened in terms of events. And then hopefully we can help librarians and historians to write history book. So what would such a history book look like? We would like to organize them based on chapters. And each chapter will look like a Wikipedia page, but it will be event-centric. So it will be talking about one major event or complex event. And we can organize them based on timeline and based on some structured knowledge. For example, who is the main actor and how the different events are connected. Some might be the condition of the other, some might be the causal, there's some causal link, and maybe some are the sub-events of another one, so you can detect some kind of knowledge in a never-ending fashion, which means this system should be run online, and then results should be updated over time, because events always evolve over time. and we may have more sources to verify our information. And then we should allow human to do editing and curation in a similar way to Wikipedia. I think this could give us much more comprehensive and more authentic summary about the history. So one example for 2019 Hong Kong protest will look like this. It's looking very similar to the news timeline. So you can see, each chapter will have a name, chapter title, it's the complex event name, and then under each title, you will see a timeline. So they are organized by the temporal relations. And then for each time point, you will see a summary about the events. So for example, the first episode is called the first big protest. And then the next one is called protest from parliament, because this one and this one, they have very different characteristics. They have different scales, different participants, and different motivation. So how do we achieve this goal? How can we make this happen, right? So like I said, the first issue is that we have been working on very low level event extraction. So we usually just look at it sentence by sentence and do sequence labeling, try to find which word is event. That's it, right? So we never look at how the events are connected to each other and how can we use that knowledge to predict what's going to happen next. So that's the first challenge I would like to talk about. And the second one is we have been so focusing on text data, and we didn't really look into multimodal data and do good fusion of this kind of information. Because as you can see from the examples, a lot of the misinformation can be verified if you gather evidence from multiple data modalities. And then finally, I would like to show a very preliminary study about how to detect misinformation on this knowledge element level instead of document level, which means you look at a document, you not only say it's true or fake, you actually detect which piece of information is fake. And then hopefully we can collect the misinformation, regenerate a narrative. So for the first challenge, let's do a little bit of recap about existing methods for information extraction. So usually we read a sentence as input, and we use embedding methods, distributional semantic representation, to encode each token, right? So 19, this word will have an embedding vector, and maybe 300 will have another vector, India will have another vector, and then we take this as input, and then we can decode a graph. So the graph will look like this. Each node can be an entity, and each edge can either be the relation between two entities or the relation between the entity and a trigger word. So trigger word means the word that indicates the event. So for example, this person is a victim of this die event. So that's edge. So we can decode this kind of edges and nodes from the input sequence using all kinds of machine learning model, for example, graph neural network. So if you look at this model, we are not looking at anything outside of the sentence, right? So we do have some contourized embedding that can teach the model the semantic representation for the token, but we won't have any idea, for example, what's a subsequent event and who else is involved in the background event. So the idea here is instead of do this kind of sequence level, sentence level decoding, we would like to look at a much broader content, look at global content. And then if we can look at millions of documents or billions of documents that are talking about similar type of events, maybe we can learn some patterns from them, because history always repeats itself. And then from those patterns, we probably can learn some lesson, and the lesson can help us not only improve our extraction of the current events, but also help us predict what's going to happen in the future. So we call this kind of pattern as schema. Schema will look like this. So this is a schema for civil unrest. And each node is a type of event, and they are organized based on different types of relations. So you can see under civil unrest, there's a hierarchical relation. You will see there's an international intervention. It's a sub-event of civil unrest. And then in each, how do you say this? Each layer, you can see the hierarchical, the temporal relation and causal relation. So for example, this international intervention is an event that happens after a coup. And so that we can see this link from coup to international intervention. And the ceasefire is a result of international intervention. So we can see there's there might be some causal relation between these two, or maybe there's another possible result. So we can also see the multiple hypotheses. For example, 20% of international intervention, there will still another coup, but 70% they will stop fighting. So why do we want to do this in an automatic way? Because we can try to cover all kinds of results, and we can learn the probabilities using machine learning model, right? So human can cover most of the frequent results, but they won't be able to write all these multiple hypotheses and try to predict the probabilities. So this task is called event schema induction. It's not new. It has been there for almost a decade, but we would like to talk about how to do this in a scalable way without using a lot of annotation, and also try to use this to improve extraction and prediction. So the model we propose is called event graph schema model. We try to look at the connection between two events through entities. So two events can be connected either because they share one entity. So for example, the attacker is the same entity as the artifact of the movement event, or because their entities have some semantic relation. So for example, the person is carrying a vehicle or is in the vehicle, and the vehicle is the instrument. So if we can make this kind of connection, we can then use it to improve the relation or event detection from the input data. So for example, if we look at this sentence, the sentence really didn't say anything about the relation between this troop and this place. But if we look at the schema will say the transportation event has an artifact, and the artifact is likely to arrive at a place, and this place becoming a target of attack. So this schema will help us infer there should be relation between these two entities. So using the schema, we encode them as global features in the sequence to graph model I just showed. And then we can see the performance of every component gets improved, especially for relation injection. So that's good news. But I guess, if we want to do misinformation detection, it would be really nice if we can prevent bad things from happening rather than wait until bad things already happened and then we report it, right? So our next goal is to move forward to make this framework be able to do prediction. So the idea is that we are going to extend the graph from just a pair of events to a big sequence or sequences of events. So for example, this person may be purchasing some materials, and they assemble the bomb, and then they put the bomb in a place, and there's attack, and after that there might be some die and injure and investigation events. So this is a much more comprehensive graph, which we call as a complex event graph. But the idea of inducing this graph is similar to what I already showed for the schema between two events. So we are going to do this step by step using a generative model. We'll start from a partial graph. So this graph is the events from new. So we already know there's attack and there's some die event after that. And then from here, we are going to predict which event is going to happen next. So for example, after this, the attacker might be arrested. So there should be arrest event. So we predict this node. And then we are going to predict a link connecting this new node with the old node. So they are connected because they share one entity. And then we are going to label the role of this entity played in the new event. And then finally, we are going to predict the entity-entity relations and temporal order. So does this event happen before or after the previous one? So the cool thing about this is that we are not only induce patterns, we also can predict the ending events or even the whole episode after we observe some existing events. So we apply this model not just to induce schemas, but also to predict ending events. So the setting here is that we are going to hide all the ending events that happen on the final day, for example, of a complex event. And then that the model predicts what's going to happen at the end. So from here, you can see we compare the results with the prediction results from human schema. So human schema only look at the most common events. So they will predict there's a sentence event, there's a child hearing. But the problem is that this person is not even arrested yet. So all of these predictions are wrong. Most of these predictions are wrong. And the human is not able to predict any probabilities because it's not data-driven method. So our model is able to predict much more reasonable events. For example, there will be arrest, and only if that arrest is true, you will see some child hearing event and a sentence event. So compared to human schema, we achieve much better accuracy in terms of event prediction. Okay, so this is the first challenge. That means we can try to extend our current state-of-the-art model from sentence level extraction to corpus level, and we do this on the prediction level, not just extracting existing information from sentence. Okay, the second challenge I would like to talk about is multi-model event extraction and inference and fusion. So from the examples I showed at the beginning, you can see images and videos are very important. 34% of information only exists in images in news articles. So we propose a new task, which is to do multi-model event injection from images and text simultaneously. So for example, here we can find the destination and agent information from the text, but we can only find the vehicle information from the image. So the problem is that we don't have any training data for this kind of multimodal task, but we do have some training data for each single data modality. We have some training data for text and we have some for image. I mean, they are not exactly the same task as what we are trying to attack, but the resources can be reused. So the idea here is to be able to construct a common semantic space to represent both the image and the text so that we can do transfer between these two data modalities. So how do we construct a common semantic space? We would like to consider image as a foreign language. And then if we can somehow translate this foreign language into some English labels, then if we look at the English text, we should be able to map these nodes and knowledge elements into the same space. So we start from collecting millions of image and caption pairs from news articles. And then for each image, we run some parser, which is called attention-based graph parsing, to get the attention heat map. So attention heat map means this region, this red region indicates there's an agent, or this part indicates there's item. And the relation connecting these different items or different entities is called throwing. So this can be done automatically in a weak supervision way or using some small amount of annotation. And then we also use object detection to detect the explicit regions. and then we merge them together. And then we use graph convolution network to encode these two graphs, and then use that to represent each bounding box or each region in the image. Okay, so for example, here, this region, we know there's a man, and this man is likely to be an agent of the throwing event. And then from this graph, we also see the man has some relation with the bus and stone. And similarly, from the text side, we will apply a semantic parser. So here we use abstract meaning representation, AMR parser, to convert the text into a graph. And then we, again, use graph convolution network to encode this graph together with the input sentence using BiOSTM. And then from this result, we can then align the labels from the images and the labels from the text. So for example, maybe the man is closer to protester and the bus is closer to other vehicle. And then from this common semantic space, we can then use that to encode or represent the training data from each data modality. So this ACE corpus is only for text, and this situational recognition corpus is only for image. And then we use this common semantic space to encode both of them. Then we train a model. So that means we are really considering this image as another language, and we just merge them into one representation. And now if we have this multimodal news, we can then apply this trained multimodal model to this multimedia news. This multimedia news may have a body text and have caption and have image. And then we can extract all the knowledge elements, entities, and events. So I'm just going to quickly show a couple of examples to show why multimodal representation is so important. So from the left image, you can see that if we ignore the text side, a state-of-the-art situational recognition system is still likely to detect this as a protest. So although these two people look super happy, right? But a regular classifier trained from that kind of data will still detect this as protest. But from the text side, you can see this is a very happy play, and there's no protest going on. Similarly, on the right side, if we ignore the image, we will fail to identify this as arrest because the word search is not a very common word for arrest. So by combining the visual features in our common semantic space, we are able to identify there's an arrest event. So doing cross-media representation is not a new idea. Many people have been trying that. For example, there's a lot of ongoing work and previous work about aligning the regions with entities, aligning pixels with characters. So the key idea in our work is to incorporate a structure. So structures are really important. So without a structure, we will fail to identify this person's role. For example, the flat representation without structure will mistakenly identify this person as agent instead of person who is being arrested. Especially when we have a bounding box that look like this, that has a crowd of people, not just individual entities, we often make mistake if we don't look at the structure. Okay, so now we can use this two new tasks for attacking the final, more exciting task, which is misinformation detection. So just to recap the motivation a little bit, at the beginning I said it's really important to figure out which piece of information is fake, right? Not just say this is fake news. Because if you look at any typical fake news document, you can see that sometimes they are changing their style a little bit, or they shift the topic. But in many cases, they try to just sneak in a incorrect fact, right? So compared to the existing work or previous work, we are looking at multimodal verification, and we are trying to detect the misinformation from knowledge element level. And we are also using a lot of structural knowledge. And we also look into the source bias and also some background knowledge. So I would like to use the Hong Kong protest example again, try to show how we do this. So this is a fake news article that has this image and the caption and the body text. So the caption says, the police is shooting at the protesters, although the image doesn't really show that. And the body text also talked about this woman, she got blinded by police, but that information is not being presented in any image or any other part of the document. So what we would like to do is to convert this whole multimedia news document into a multimedia knowledge graph that will look like this using the technique I mentioned. We identify entities and we extract events from the multiple data modalities, put them together, and then we also link the entities into some external knowledge bases such as Wikipedia. And then we can use graph neural network again to encode this multimedia knowledge graph, and then we can classify this whole graph, or maybe each triplet inside this graph as true or fake, right? So that's the whole task. And if we break down the graph into triplets, we are basically looking at 2 nodes and the edge and try to classify that triplet as a real or fake. So this is an example for this news document. You can see all of these triplets are fake. Okay, so how can we do this? First of all, we need to construct this graph. From the multimedia event injection, we can have that results for each data modality, but we also need to do some cross-media grounding so that we know the place identified from image is the same place that mentioned in the caption. So we also do cross-media event coreference and the entity coreference to merge them into one graph. And then within each data modality, for example, for the graph from image, we'll do verification, which will check whether the nodes and edges are consistent. And then between the images and article, or between article and caption, we also do cross-media verification to see whether they are coherent, whether they are talking about the same thing, whether the rows are the same thing, and use that as features for classification. So this all sounds really nice, but I'm assuming we have training data, right? But the problem is we don't have training data because most of the fake news documents are being removed immediately once they show up. So I would like to propose a new idea to generate training data automatically. Because of the interest of time, I'm just going to skip some details just to show you some examples. So the whole idea is that we are going to manipulate the graph. We are trying to mimic how humans generate fake news. So we are going to take our real news document as input and construct a knowledge graph, and then manipulate the knowledge graph by switching the entities, replace some of the edges and entities with a new one. So for example, here we're going to replace the country name Zambia with Fiji, because Fiji is semantically similar to Zambia, and they share some properties. And we're not going to replace the bicycle because bicycle is already shown in the image. It's too easy to detect. And then we use graph to text generation to generate a new article, and then use this for training. Okay, and we also use another AMR, semantic parsing graph, to do similar manipulation for captions, including sentiment and also negation manipulation. So this is a very powerful idea actually, because we did a tooling test. We asked a human to look at the pairs of the original real article and the fake document we generated, just like I did for the quiz at the beginning. So human is only able to identify about 42% of the fake documents. But don't worry, we are not going to share the generator with anyone. We're only going to share the detector. So we're not going to produce any fake information. So we apply this model to the existing data sets from Boston University last year NLP paper, and also the UW paper called Grover. So these models, they only use sequence-to-sequence generation to generate the fake documents, and they use some features which is only based on language, and it's not using knowledge graph. So our model performs better, and we can also see for the knowledge element level detection, the performance is decent and is better than the random baseline. But of course, there's a big room to improve for this task. It's still a very big challenge if you want to detect the knowledge element. And this is just another example to show quickly that we detect this as a fake information because this facility is not grounded into the body text. So ultimately, we would like to further collect the information and really generate an authentic story, and also incorporate some background knowledge from the source, and do also look at the source bias. So I won't have time to show any demo, but I will share the slides publicly so that you can play with it. And all the software is also available as Docker container and open source, and you can feel free to use them. And I would like to ask everyone to join me for this great effort. I mean, it's a very challenging, very crazy task, very complex task, but I think it's very important. And in the future, we would like to tackle the things I already talked about, background knowledge, and also do narrative generation. Yeah, thank you. I would like to take some questions if I still have time.
Sure, we have. Thank you so much for the very interesting talk. We have several questions here. I'm just going to ask people that are in the Zoom, if you want to say the question yourself or pose the question yourself, can you raise your hand so we can call on you? And if you prefer that we read them, we can definitely read them as well. So let's see. We'll start with. I'll see if someone has raised their hand. Okay, so we do have questions already. So the first question is from Jessica Sarai Mendez Rincon. She's asking what machine learning techniques to apply to predict in a graph.
Yeah, so the framework is called graph generation. I can send more details, but the whole idea is consider the graph as if you flatten the graph as a sequence, right? For example, if you do breadth first search, you can flatten the graph into sequence, and this just becomes a natural language generation problem. So you can consider, for example, the first node is a token, and the edge following that node is another token. So you can flatten the graph into sequence. And if you already observe a lot of graphs from the historical data, you can train this generation model from that data. So then in the new scenario, once you have observed the new node, this generation model will generate the next node and the next link. Is that clear, or should I elaborate more using examples maybe?
I think that was very clear to me. We can let Jessica can let us know if she wants you to expand on that. In the meantime, we have another question from Anibal Arias. He's asking whether these graph models can predict crime events in a city.
Yeah, that's one of the applications. We want to do that. That's that's a very big scenario we want to predict, and hopefully we can remove the bomb in time, or even arrest the person when they were still purchasing materials to make the bomb. Yeah, so basically human disaster and natural disaster are the two big scenarios that we are applying our techniques to. We are also predicting the events in pandemic, for example. If you observe some restaurants closed, then we can predict maybe we should provide more food supply in supermarket. Yeah.
That sounds like the movie, the Minority Report movie, right? The Tom Cruise movie where they were predicting the crime scene. arresting people before it happens. I mean, there's some very good aspects of that, but it's also a little bit scary, to be honest. Okay, so there is another question by Iman Jundi. He's asking, in news articles, many images are used as visual aid to appeal to the readers and not as evidence for the news. Some are still circulated in fake news as evidence. How can we still differentiate between both cases?
Yeah, this is a great question. It's also a big challenge. So our solution for one strategy is to look at the cross-media grounding. So if there's some substantial amount of entities in the image can be grounded into the caption and body text, that usually indicates the entities are important or relevant to the topic. But if very few entities can be grounded or very few events can be grounded, then that image, yes, it's usually just some illustration of the topic, or maybe just to provide some additional background information. But we found in most cases in news articles, the images and the captions and the body text, they are complementary, and they do share some crucial entities for involving these stories. Yeah. But
Okay.
It's a very good question. I think we need to improve that part, need to distinguish these two cases. Yeah.
But related to that, I'm also wondering, so what if the image is fake?
The event is fake?
No, yes, the image, like that you're analyzing and finding relationships within the image evidence and textual evidence. So what if your image is fake?
Yeah, so so my team did not do any work yet on fake images, but in our team, bigger team for this project, so there are some researchers from Albany and also from University of Michigan. They have been looking into fake image detection. So the idea is similar. So we still try to incorporate some background information from text and try to see how much information is consistent between data modalities. And they have some lower level features they can leverage for detecting fake images. So that will be used as well. And also we are looking at cross image verification, looking at multiple sources. Yeah, but it's very hard. Actually, fake videos are even more challenging than fake images.
Yeah, can imagine. So, Elena, you want to ask your question? There's a question by Elena, but she's one of our organizers. So,
hi.
Hi, Elena.
Hi, Heng. Yes. Okay. Well, I was wondering, when you are building your synthetic data set, are you introducing some bias in the corpus? I mean, you are building a data set that is already prepared to work with the architecture you're proposing. So I was wondering if you also test your model with any real fake news corpus?
Yeah, that's the best question that I have ever received whenever I gave this talk. I was trying to hide that result. I didn't show you, but we tried, and the detection accuracy is much lower than what I'm showing here. So we tried the same model to detect the human written fake news. The detection accuracy is around 50%, 60% for document level. So it's not good. It's it's much lower than what we can achieve on the machine generated fake news. So the challenge here is manipulating facts is only one aspect that the human usually do when they generate misinformation, because they often consider other aspects. For example, they will introduce some details. They will make up some new entities. So that kind of thing cannot be simulated in our current synthesis framework. So you are right. We not only observe the bias between human generated data and machine generated fake news, but also if you look at these two different data sets, right? So this one is from the Grover generation, and this one is what we generated from Notch graph. Even between these two data sets, you can see very different performance for the same model. Yeah, so and also depends on what other real documents where did they come from, right? So we tried our experiments on Voice of America. That's apparently not enough, right? Because it's only one single data source. Yeah, so I think in the future we really need to implement more tricks that human usually do, and also aggregate all the possible sources for the same topic. And yeah.
Thank you for that. So
Thank you,
there's
Ken.
a question.
Yeah.
Sorry, a question by Angelina Espejel Trujillo. She's asking about whether you have tested your system in different, or your research in different languages other than English.
Yeah, we are working on English, Chinese, and Spanish right now for the pandemic scenario, because there's just so much still ongoing misinformation, and I personally want to do Chinese, and I have some students who are Spanish native speakers, so they want to do Spanish. So yeah, so we are working on that. Hopefully there will be some results out by the end of the summer. Yeah.
We're looking forward to those results in other languages. We do need misinformation check in Spanish for sure. So there's another question by Santiago Incapié. Any idea on how to include video information? I mean, in social networks, there are a large number of public complaints in this format. Do you think it is possible to improve the model using this information?
Yes, definitely. And I think it's harder to detect fake videos compared to fake images. So my collaborator, Professor Steve Chang's group, they have been working on cross video and text event co-reference resolution. So the multimodal model that I presented has been already extended to videos, but we haven't used that additional evidence to detect misinformation from video yet. So the biggest challenge there is how to you make sure that from which key frame to which key frame is about the same event. So the boundaries of events, and also the detecting the roles entities played in event are much more challenging than images, because you will need to analyze the whole action and things like that. And there's not much training data available for that task either. Yeah, but definitely that's one of the most important future work. Yeah.
Yeah, more work to be done in that area. Okay. So for the young researchers, there's a lot to do in this space. Let's say one last question before we go for a break. Ricardo Muñoz Sanchez, he's commenting about, the unknown, unwanted biases in a lot of the technology, right? But this is talking about predictive policing. So some of the systems that are predicting events can be related to policing, right? Or security. How will this approach avoid replicating those systemic biases that we know exist?
Yeah, so like I said, in the current finished work I presented, we didn't look into this profile for the source, right? So we actually also, we do have some source information that we use, so that we include the news agency, the journalist name, which is like here, right? So we'll use the location, the news agency, and some meta information. I mean, for example, the journalist name. So we do have this as part of our graph, and then hopefully, for example, if the training data shows this person, this journalist tend to post misinformation for what kind of scenario, then hopefully the model can learn that. But our ongoing work is trying to look at very fine-grained dimensions of the bias. Like, you know, the journalists may have political stance, they may have their own aspects they want to focus for a certain type of event, and they, you know, may have different degree of emotion, sentiment, expression, things like that. So we are looking into how to capture that bias from both the source side and also the receiver, means the user, right? Yeah. So yeah, it's not part of our current project yet, but we are actively working on that.
Okay, so
Yeah,
that's another interesting line of research for future work. All right, so with that, thank you so much, Professor Hengji, for this wonderful talk. We appreciate the time. Thank you for all participants, for your questions and joining us. We'll take a very short break of 2 minutes to stretch our legs, and we'll be right back with our next talk. Okay?
Thank you very much.
Thank you.
Sorry for the delay.
You're fine. And Samuel, I think you will take it from here, right? I see that our next speaker is already here.
I'm good. Hello, you can hear me and all?
Yeah,
yes.
Okay. So we take a few minutes to start your conference. So we are here. If you want to share your slides to test or?
Oh, sure. Okay, so let me do that. So then I'm doing the Zoom. Okay, is that working?
Yeah, that's good.
Awesome.
Perfect.
Should I put it back down again for the moment? I'll leave it up.
You can leave it up if you want, Dr. Marin.
Okay, 1 minute and we start. This is the team of organizer of the summer school. Chris is Tamar Solorio, Gabriela, Esau, Elena, Iram.
Hello, how are you?
Hi, how are you?
We can start, Elena?
Yes, Samuel, you can start. We are transmitting live.
Okay, thank you. So I will give the introduction. Good morning, everyone. Welcome, Dr. Christopher, to Mexican LP Summer School 2021. We appreciate the time you took for this talk. I will give a brief introduction of the curriculum of Dr. Christopher. Christopher Manning is the inaugural Thomas M. Siebel Professor in Machine Learning in the Department of Computer Science and Linguistic at Stanford University and Director of the Stanford Artificial Intelligence Laboratory. His research goal is computers that can intelligently process, understand, and generate human language material. Manning is a leader in applied deep learning to natural language processing, with well-known research on 3 recursive neural networks, the globe model of core vectors, sentiment analysis, neural network dependency parsing, neural machine translation, question answering, and deep language understanding. He also focuses on computational linguistic approach, robust textual inference, and multilingual language processing, including being a principal developer of Stanford dependencies and universal dependencies. He is an ACM, AAI, and ACL fellow, and a past president of the ACL. His research has won ACL, Cooling, NLP, and CH-based paper awards. He has a bachelor from the Australian National University and PhD from Stanford in 1994. And he held faculty positions at Carnegie Mellon University and the University of Sydney before returning to Stanford. He's the founder of the Stanford LP Group and managed development of the standard core NLP software. Well, the talk for today is large language models, linguistic structure discovery, and more efficient training. So for all attendees, your question can be placed in the specific space. Also, for those who see us on the YouTube channel, you can place your question and we will ask to Dr. Chris when end the conference. Again, thank you, Dr. Chris, and you can start with the conference.
Thank you very much for that lovely introduction. And hello, everybody. It's wonderful to get a chance to be here at the Mexican NLP Summer School. So the main topic I'm going to talk about today is some of our recent work looking at the large pre-trained language models like BERT, Roberta, XLM that have made such big changes to the NLP world in recent years. But I wanted to take some time to think about this in the broader stretch of history of linguistics and NLP. In some ways, what we're seeing happening now in NLP with these recent developments is the more recent episodes of what's actually a long-running drama series that goes back to the 1950s. So starting in the 1950s, Noam Chomsky developed and argued for an articulated syntactic deep structure for language, and in particular argued against any utility for work proceeding from the frequency of linguistic units in speech or text. So he said, but it must be recognized that the notion of probability of a sentence is an entirely useless one under any known interpretation of this term. In contrast to this, Claude Shannon was developing information theory, which not only underlies us being able to have video conferences today, but he argued the opposite. Anyone speaking a language possesses implicitly an enormous knowledge of the statistics of the language, enabling them to complete an unfinished phrase. These ideas have proven to be incredibly useful in both natural language processing applications, but also in other areas such as psycholinguistics investigations. So the key idea that has developed and has only become more prominent in recent years is this idea of language modeling. So a language model predicts a word in a context. So after the students open there, we're giving a distribution over what words are likely to come next: books, laptops, minds, perhaps. And so we do this by putting a probability distribution over different words that follow. And these language models have long been a key part of decoding tasks like speech recognition and spelling correction and in machine translation. But they've achieved new prominence in recent years because these current large language models essentially use language modeling as their underlying basis for learning about language in general. And that's given them new abilities to do language generation tasks like summarization and story generation. So for what I'll call now the dark ages, last century, or really up to about 2012 12 or something, by and large, the way we built language models was called n-gram models, and that this was pretty simple. What we did was that we just counted up how often sequence of words like the students opened their books occurred, and then we divided through by the number of times the students opened their occurred, and that gave us a relative frequency, which we interpreted as a probability. So this was a simple model, but it was really rather a bad model because it had the classic cursive dimensionality disadvantage, that this meant that you got humongous numbers of parameters. And about the only way you could control the context number of parameters was by limiting the amount of context you conditioned on. So rather than predicting the next word based on the students opened there, you might predict it only on the previous 2 words opened there. But even then, there were lots of problems with the sparseness of the data. We just couldn't see enough language data to account for the creativity of language. And so people used other techniques such as discounting or smoothing techniques and mixture or back-off models to try and get some halfway good probabilistic data about how likely different words are to follow. But despite that, these models were already incredibly powerful, so that they laid the basis for things starting to work in the 2000s decade. So in terms of whether it's speech recognition or something like the early generations of Google Translate. Because it turns out that once you start conditioning on a few words of context, things already just about begin to work. So if it's just 1 gram's word frequency, you get sort of junk, to him swallowed, confess here both. This is a language model trained on Shakespeare's plays. But once you get up to just even a couple of words of context, such as a 3 gram model, fly and will rid me these news of price, therefore the sadness of parting, you already get something that has a reasonable approximation of the grammatical structure of a language. So it often looks syntactically okay, but semantically it wasn't really there. And the question is, was this teaching us anything about human languages? And in that period, by and large, when linguists became aware of the kind of work that was being done in statistical natural language processing or speech recognition, their reaction was really, no, this doesn't tell us anything about the structure of human languages, that even though these n-gram models know quite a bit of simple world knowledge, and in a certain way, they know about low-level syntax because they've got facts in their probabilities about, in English, you get sequences like preposition, article, noun, and article, adjective, noun. They don't have any concepts. They don't know about the concept of noun. They don't know about the sentence structure rules like phrase structure rules, context-free grammar rules that people are used to seeing in grammars. And so these models were viewed as completely linguistically uninteresting. And so in the 1990s, the solution, which was broadly pursued in natural language processing circles as well, is to say we have to start building models that understand the hidden latent structure that underlies a sequence of words in human languages. And so that led to big efforts and big investments to build annotated data sources like tree banks. So here's a picture of a tree from the Penn Tree Bank. But that seemed very successful, and really through the 1990s and the 2000s decade, that was the mainstay of everything that we were doing in NLP, often with quite a bit of success for different applications. But in the meantime, there then emerged these neural language models, and that they had 2 big advantages. The first was that they solved the curse of dimensionality, because once we started representing a word not as a symbol, but as a medium dimensionality, real numbered word vector, well, then we could have different words share their similarities via vector similarities. And so we no longer have the curse of dimensionality. And fairly soon after that, people started to explore recurrent neural network models. And then this, for the first time, provided a way that we could build language models that were aware of long context. And there are many cases when that's just really necessary. So here's a sentence from an Arthur Miller play: "The same stump which had impaled the car of many a guest in the past 30 years, and which he refused to have." To guess which word is going to come next, he refused to have just isn't much of a clue. I mean, maybe it's he refused to have an operation, he refused to have a holiday. You're not going to say he refused to have removed, unless you've looked much further back to see the discussion of the stump which had impaled the car. So in this new world, words were now being represented as vectors in a vector space. And what people started to explore was unsupervised or self-supervised methods by which you can learn these vectors for words. And it turned out that there were good algorithms where words could be placed in a vector space by a neural network learning algorithm so that they end up in positions reflecting their semantic and syntactic similarity. So you get not only areas where country names and verbs are, but you actually get good fine structure inside that. So you have the various forms of the verb to be down in the bottom right, other verbs that are copular verbs like become and remain are next to them, verbs that take sentential complements like say, think, and expect gather together in the over on the left side, and so on. And so this then led into building these recurrent models which could predict which word came next. I'm not going to go through all the details of that, but the interesting thing that happened was at the start, we had word vectors for individual words in a context-free way. But once people were starting to build these predictive models like RNN models, people started to notice and realize the fact that we could regard hidden states of these models as a context-sensitive representation of a word like opened. So the circled vector can be regarded as a representation of open in the context of the student's blank there. And this then gives us contextual word representations. And that's proven to be an incredibly powerful idea because the meanings of words change a lot in their context of use. That was an idea that traditionally was handled by mechanisms like suggesting word sensors, but word sensors were always a fairly imperfect way of capturing the way that the meaning of words changes quite fluidly in a context. So that's the long history. If we sort of jump forward to the last 3 years, we've then seen these dramatic advances in huge language models. So it started off in 2018 with the ELMO and the OLMFIT models, which were still recurrent neural networks. And then things proceeded very quickly with the GPT model from OpenAI, the BERT model from Google, which maybe is still the most famous one, GPT-2, and then sort of floodgates of lots of models, XLNet, Ernie, Grover, Albert, T5, Roberta, GPT-3. And these came along with the adoption of a new technology. So all of these more recent models stop being classic recurrent neural networks and become transformer models. And these new models start to be able to produce very fluent text that wasn't only grammatical, but actually made sense and could maintain context for a long period of time. So in these kind of examples, a human is writing a prompt as a first sentence: a train carriage containing controlled nuclear materials was stolen in Cincinnati today. And then the model is generating text to follow that. And this is GPT-2. The incident occurred on the downtown train line, which runs from Covington and Ashland stations. In an email to Ohio news outlets, the US Department of Energy said it is working with the Federal Railroad Administration to find the thief. And so what you can see here is not only is the text perfect in terms of being grammatical, good English, but we see that the sentences are semantically coherent, and there's a discourse flow and reference to real world context that's just maintained extremely well. So from the prompt of nuclear material stolen, GPT-2, just from reading a lot of text effectively in its training method, it just knows a lot of facts. So it knows that Cincinnati is in Ohio, so it mentions Ohio news outlets. It knows that in the United States of America, that the Department of Energy is responsible for controlling nuclear materials. So it brings up the Department of Energy. Since there's mention of was stolen, it mentions a thief and a theft. It's just all very coherent and good. Okay, and so this has then led to this new very common model of building different applications where what you're doing is you're starting off with one of these large pre-trained language models, such as here, the BERT model, and then there are particular tasks that you want to do. You might want to do question answering or named entity recognition or a natural language inference task. And then people are taking this large pre-trained model and fine-tuning it for particular tasks on top. And the reason why there was this huge move to transformer models was it's a slightly complex story, and there are various aspects of it which I probably don't have time to explain all of, but a large part of it is that this gave a huge boost in scalability and efficiency of models. So despite the fact that deep learning had eagerly adopted GPUs, which were meant to offer fast parallel computation, there was always a problem with recurrent neural networks that actually you had to do this sequential computation along the sequence. So transformer models get rid of the sort of sequential processing, and instead they process all words of text simultaneously. And the way they achieve still incorporating context is at each level, they have a hidden representation, which starts off roughly as a word vector. And from there, you're calculating projections of a query key and a value. And these queries are used in an attention operation to look at the context everywhere else in the sentence and to incorporate that into a new value for the hidden state at that position. And then the transformer models are essentially using this powerful idea of attention as much as possible. So at each layer of a transformer network, you're not just doing one attention calculation, you're instead defining 12 different key query and value projections. So you can get 12 attention projections, which are combined together for the next hidden state. And then you just repeat that over and over again, say 12 times. And so you end up with these representations of words that have a very rich understanding of the context that's around them. And these models have been super successful. So this is going back in time till 2017 when the squad question answering challenge started. So this is sort of passage. Here's a question: which team won Super Bowl 50? And the answer is the Denver Broncos. And when things started off, people were very quickly able to build neural models that worked much better than a traditional symbolic feature-based NLP model. So going from 51% to scores in the 70s, and the scores were gradually getting better, but they were a very long way away from the scores of human performance or 100%. But once BERT came along, BERT just really pushed up the scores on these models. And so very quickly, the only way that you could do well on the leaderboard was to make use of BERT. And you were then getting scores for the F1 measure, say, of 87.5%, which was kind of getting close to human performance of 89.5%. And since that time, things have only gone on. There have been much bigger pre-trained language models, XLNet, Roberta, etc., and the scores for the systems are actually exceeding now what was measured for human performance. And it's been very useful in industrial applications as well. So Google regards using BERT models as the single biggest improvement in their search engine performance since the original introduction of PageRank ideas. So what I now wanted to tell you something about is some work that was done by some of my students and others, Kevin Clark, John Hewitt, Urvashi Khandelwal, and Omar Levy and me, which was looking at, well, how are these big pre-trained models able to be so successful and get everything right? And so what we wanted to do was understand more of what does a BERT model know. So a BERT model calculates these context-dependent word representations. And so for each word, for each of its attention heads, a simple thing that we could do is just look at what the attention head is looking at. And that might give us some idea of how much the model understands. In particular, do attention heads learn to look at the linguistic structure of a sentence in the way that makes sense to human beings based on what we've discovered of the linguistic structure of human languages? And the answer to that is yes. If you look down the bottom of a BERT network, well, it's mainly doing pretty obvious things. So there are heads that attend broadly as sort of bag of words heads, but that makes sense because you just want to understand the overall context of the sentence. And there are heads that attend to the next and to the previous word. And, you know, that makes sense as a simple strategy because those are if you want to know the single place where you can find the most information is looking at the word to the left and the right on average. But once you go up into the higher levels of a transformer network, there's actually a lot of structure, a lot of attention heads that pay attention to syntactic structure. So something that we could do is we could look at the dependency structure of a sentence. So here we have went having a subject of I and a prepositional object, a preposition. The prepositional object is to the store. And we can then ask whether attention of various attention heads in a BERT model are doing the same things as discovering these syntactic dependencies. And the answer is basically yes. So once you're into the deeper layers of a BERT network, you find lots of heads that are basically learning to look at stuff in a syntactic structure dependent way. So the 10th head on the 8th layer of a BERT network, it has direct objects attending to their verbs. So for Payne-Weber considered an even harder sell, recommending specific stocks, you have sell attending to considered and stocks attending to recommended. It's strictly not only the noun head of the object that's attending. So really every word in an even harder sell is attending back to considered. Oops. And then for the example on the right, the 11th attention head at the 8th layer, it has noun pre-modifiers attending to the head. So the complicated language in the new law, so the uncomplicated attend to language. In the new law, in the huge new law, all of in the huge new attend to law. And sort of interestingly, you find that sort of prepositions before the noun phrase are also attending to the noun. So that's sort of like the idea in generative grammar of extended projection that Jane Grimshaw suggested. So simply by using these heads, you can already actually build a pretty decent dependency parser by just taking the information about what the heads look at. Interestingly, there are also some higher level linguistic things. So the 4th head at the 5th level is basically a co-reference head. So with Kim today, as she got some expert opinions on the damage to her home, we see that she attends to Kim, she, and her attends to she, and more weakly back to Kim, so that the co-referent words in this sentence are all attending to each other. And that doesn't only apply to pronouns. You also get it in cases including across sentences, like joining peace talks between Israel and the Palestinians. The negotiations are, and negotiations and talks both attend to each other. So we wanted to push that idea somewhat further. And so we wondered whether you could actually say that a BERT model is actually doing its own syntactic parsing. It's building up structure of the structure of a sentence that can make use of in working out the meanings of words and context, and for correctly predicting words and context as a language model. And so to do that, you had to come up with a way that you could look at these contextual word vectors and get out of them a tree structure of the kind that's hypothesized for the syntax of languages. And on the surface, that seems pretty difficult because real valued vectors don't seem to look like the symbolic operations of trees. But working together with my student, John Hewitt, we came up with the idea that there's actually an easy way to unify the two, which is through the idea of distance metrics. So for a vector, there's a distance between two vectors, which is the have regular Euclidean distances. But for a tree, they also have a distance relation between words, which is the path metric of how far words are apart. So chef to was distance 1, is close by, where store to was is far away in the syntax tree. It's of a distance 1, 2, 3, 4. And so that reflects the fact that although in this sentence, the chef who ran to the store was out of food, that even though the word store is next to was, it's not that the store was out of food, because the syntactic structure says otherwise, that's captured by the distance. So that suggested that what we should do is look for a distance measure in the vector space that is capturing syntactic distance. Well, to do that, it seems like we can't just use the entire word vectors, because word vectors encode a lot of stuff. I mean, in particular, they encode all of word and sentence meaning. Presumably, the syntactic representations are a pretty limited part of what's represented in the vector space. So what we'd like to do is find a subspace that's encoding syntax. And so we want to find a linear transformation onto a low-dimensional subspace, which is the syntax subspace. And then our hope is we can do that in such a way that distances in that subspace, and strictly we use the squared vector space distance for a technical reason, will correspond to the tree distance. And well, to the extent that that's true, we can then recover the syntactic tree of a sentence by simply creating a minimum spanning tree in this subspace. And so the question is, does that work? And so to find out if it works, what we do is to say, can we find a single transformation matrix to a low-dimensional subspace such that over all sentences in a tree bank, if we learn a good B, we'll then have a good distance metric that'll give us tree distance. And if you try to do that, what you find out is that for simple representations, it doesn't work very well. Even for BISDM level representations, it doesn't work very well. But for modern transformer-based models, such as BERT model, and indeed you can get even higher numbers for some of the more recent models, that largely we can recover the syntactic structure out of the vector space, so that if we ask for the minimum spanning tree, it gives almost exactly, it's a little bit wrong over here, the same syntactic structure for the sentence as the human linguist gave. And so effectively, these pre-trained contextual language models are discovering the syntax of human language sentences that effectively, once you've built big enough models, it's just useful for them in terms of being able to predict the next word, to know about the syntax of human languages, And so they make use of that and learn about that because it just helps the power of the model. And so that's actually sort of a fairly incredible thing, that this complex latent syntactic structure that human linguists have spent decades working on is really just becoming revealed by a model with this very simple objective of predicting a word in context. It doesn't only work for English, you can do it for other languages. And then actually, interestingly, if you do it for multilingual word spaces, you can see interesting correspondences across different languages, which let you see the commonality of different grammatical relations across languages. So we posed this question of, does a model like BERT learn about human language syntax? And we looked at a couple of ways that you can evaluate that. And the answer is that yes, entire parse trees are quite accurately embedded in the representations of large pre-trained language models. So that's a central result of how we have language discovery. I now want to spend a few minutes telling you about one other thing, which is some work that Kevin has done together with a couple of people from Google, Tang Luong, Kwok Le, on coming up with a different way of training these large pre-trained language models that is more efficient to use. Because if you remember back for when I had the slide showing all the transformer models, I didn't emphasize it at the time, but the problem with these models is that they're extremely expensive to train. So let me just illustrate that idea. I'm going to illustrate it with statistics on this GLUE benchmark. So the GLUE benchmark was proposed by Sam Bowman and colleagues in 2018 as a range of natural language understanding semantic tasks that models could be evaluated on broadly. There are various tasks of sentiment and sentence similarity, but the most common kind of task is effectively these natural language inference tasks, where you're judging whether a hypothesis contradicts, follows from, or is unknown with respect to a premise. So if the premise is hills and mountains are especially sanctified in Jainism, then that contradicts the hypothesis, Jainism hates nature. Since it was proposed in 2018, a huge amount of progress has been made on this task. So we've gone from, what might now be called traditional deep learning models of the mid-2010s, ones using gloved word vectors and methods like convolutional or recurrent neural networks, which were then getting sort of about 68% GLUE score. As we went through Elmo, GPT, the BERT models, XLNet, Roberta, Albert, the errors have reduced by about 3 times, and we're over 90% performance. And indeed, again, it's the case that this can be claimed to be superhuman performance because these models are getting the answer right more often than when you give these puzzles to human beings to do. So that looks like an amazing success story of natural language processing. But if you then change the axis and then start saying, well, let's actually look at how much computation is needed to train the models to get these results, then the results don't look quite so good. So now on the x-axis, we've got floating point operations to train the models, and still on the y-axis, we've got GLUE score. So on this graph, a glove-based model or an Elmo-based model takes almost no computation, so to speak, and does respectably well. And then as you start building these bigger pre-trained language models, you start to do a bit better. But now what you notice is that going from, say, BERT-based to BERT-large, you're hugely expanding the model and the amount of computation required, and you're getting a fairly modest increase. So to put some numbers on this, we're into sort of the very big numbers of exaflops and zetaflops. So this is sort of 64 exaflops, 6.4 times 10 to the 19 flops. And then to go up to BERT large, you're then increasing yet further the flops. So BERT large is already using 60 times as much compute as Elmo to get its gains. But that was really only the start of things, because then after BERT came models like XLNet, and Roberta is up there with 3 times 10 to the 21 flops. So Roberta is using 16 times more compute than BERT large. And things were just continued from there. So then there are models like Albert that's using 3 times 10 to the 22 flops. And so sort of all the classic models are just sort of being squished against the y-axis because of the sort of exponential scale with which the computer is going up. And so what we'd really like to know is, could we have models that are aiming sort of more up in this top left, where they work well, but use relatively less compute? Because rather than the slogan, AI is the new electricity, we seem to be at the moment in this world where the slogan is rather electricity is the new AI. The more electricity and compute power and data you throw at the models are getting better, but it's not really that the design of the models has been getting better since the development of transformers. So Kevin came up with this idea that we could maybe do better by changing the method of language model pre-training. So up until then, there'd been 2 methods that have been widely used. So there's the classic method of language models where you're predicting the next word. So based on the artist, you're predicting the next word sold. Based on the artist sold, you're predicting the next word that, and so on. BERT introduced this different idea of doing masked language modeling. So you masked out certain words in the input, and then you try to predict them based on a double-sided context. So if the first mask is predicted to be artist, and the second mask is predicted to be painting. So Kevin's idea was, rather than doing that, we could instead corrupt the input somewhat by replacing some words with a semantically similar word. So we could perhaps replace painting, replace artist with painter, and painting with car. And then what we'd do is give the model the job of saying which tokens we'd replaced. So it simply has to say original or replace for each token. And this gives you 2 wins. One win is you're now learning from every word in the sentence, whereas in the masked language model world, you're only actually learning from the words that are masked, which is about 15% of the words in the sentence. And the other way that you're winning is at the end, you just have a binary classification. And actually in these models, doing very large softmaxes at the end to predict words is also expensive. So the style of this model is you have a small model, which might actually typically be a small masked language model, which can predict likely alternative words. And then there's a larger discriminator model that's trying to decide replaced or original. And these 2 models are trained jointly, but after we've trained them, we simply throw away the generator and use what's in the discriminator as our language model to get contextual word representations. And so this turns out to actually be pretty successful. So we can actually make quite meaningful progress at pushing things out into this top left of the graph, where we're able to get models that perform very well. So this Electra large model performs about as well as Roberta, while using a fraction of the compute of Roberta. And indeed, you can be getting models that are considerably better than BERT large, using very little well, relatively speaking, very little computation at all. So here are a few numbers on that. So if we build big Electra models using the same amount of compute as BERT large, we can train a model that's a little bit better than a much larger XLNet model. But perhaps more interestingly, for those of us who work in academia, you can go in the other direction and build very small models. So if we sort of head downwards, we can build and what's called here the Electra 25% model, so 25% of Electra small, and it trains in pretty little time, so 1/181st of the time to train BERT base, but still performs as well as the Distilbert model that people often use when they want to be a bit resource constrained. And so it's small enough that you can train it in one day on 1v100 GPU, which is a pretty nice place to be if you're wanting to be an academic training these kind of models. Yeah, so that's sort of particular work on trying to push those along. For my final thought, I just wanted to return to this theme of the history of linguistics and NLP and what we seem to be achieving right now with these modern large models. We've shown that unsupervised or self-supervised learning of linguistic structure can now be done very successfully with these models. And indeed, what we seem to have discovered is that these deep contextual word representations have stopped being just things that learn statistical associations like an n-gram model, but they've actually become models that discover the structure of human languages, that when you're training these models on enough data with enough parameters, that they actually turn into language discovery devices, so that these large models are actually learning the syntactic structure of human languages and semantic phenomena like co-reference as they go. And that's actually just, I think, not only great for having much more powerful NLP models than we used to have, but it's also a really interesting idea from a linguistic perspective. So if you go back in the history of linguistics, that in the 1940s and 50s, before the rise of Chomsky generative grammar, that period of a late American structuralism was sometimes referred to as distributionalism. It was sort of a somewhat distinct school of thought from European structuralism. And the idea that they had was what linguistic science should be doing is to try and work out a discovery procedure for human languages. So starting from the bottom up, you'd have spoken language, you'd be finding the phonemes of a language, and then you'd be starting to find the pieces of words, the morphology for the different inflections of words. And you could build a discovery procedure that would gradually work up to find the syntax of words. That was the idea, but in truth, they sort of basically had no idea of how to do this. And well, to be fair, I mean, back in the 40s and 50s, there was essentially no understanding of how to do machine learning of any sort. So that's perhaps not too surprising. But really, with the kind of distributional learning that we see in modern NLP, people are actually taking an idea like that and showing how to make it work. So when Chomsky appeared on the scene in the later 1950s, explicitly he laid out the position of different possible requirements of a theory, and he said that a theory of grammar could provide a practical and mechanical method for actually constructing the grammar given a corpus of utterances. That is a discovery procedure for grammars. And Chomsky wanted to argue that that was an impossible expectation for a theory of linguistic structure, which leads into the kind of general generative approach that he pursued for decades of assuming the importance of innate linguistic structure and so on. But actually now, with these recent models, we seem to have mechanical discovery procedures that can learn the syntax as they work from a corpus, which is a rather powerful idea, which I hope people will start to pay attention to in linguistics as well as NLP. Thank you.
Thank you, Dr. Chris.
Yeah.
Now we can start some questions. Emmanuel Rosillo have a question. What was the tag SAP?
Sorry. Yeah, sorry. Yeah. Sorry, that took me a minute to connect it up, but I got it now. Okay, so there are some particular details of how the BERT model was trained and set up, and if you're going to work with these models, you sort of have to learn all of these details. So, so for the representation BERT uses for a piece of text, it adds in some extra tokens. One thing is that right at the beginning, it adds in an extra pseudo token that's CLS, a class token, which is widely used to use as a representation of the whole text and things like classification. But in addition to that, in the original BERT model, there was this extra element where it wasn't only predicting masked words, but it also wanted to predict whether two pieces of text did or did not follow each other, like had it been taken as two consecutive pieces of text, or had it taken two random pieces of text and stuck them next to each other. And I think the reason they put that in was that they were hoping that having that extra task would cause the model to learn more higher level discourse structure. That's been investigated more recently, and it seems like actually that's not very important or useful in the original BERT formulation, though people have tried some different formulations. At any rate, there was this extra SEP token, and the SEP token is placed between the two pieces of text. In a way, it's just this artifact that's there. When you look at the attention maps, though, you see interesting things happening that often attention seems to go to SEP. Effectively, actually, that seems to represent that the head is turning itself off. So something like a head that has the object look at the verb. Well, if the words aren't words in the object, commonly that head will just look at the SEP token, which means I'm doing nothing.
Thank you. We have another question. This is from Manuel Montes. You mentioned some limitation of the classical language models, but what do you think about the limitation or drawbacks of these new large language models? In addition, the cost of computing.
Yeah, in some sense, that's maybe a hard question because they work so well. Yeah, so, I mean, there's clearly the disadvantage of the cost of computing in terms of amount of computation and the size of the models. There's another sense in which you could say, oh, it's hard to find a disadvantage because basically for any NLP task now, we can build systems using these models that just work much better than what we had before. And indeed, that's a lot of what you're seeing as people are discarding any systems that use older models and rebuilding them around these models. But I don't think that means that there are no disadvantages and drawbacks. So to highlight a couple of them, I mean, one is that these models are pretty impenetrable, that somehow they've worked fantastically well, but it's often actually really rather difficult to see what they're doing and how. And that's sort of both frustrating as to a human observer, but also means that you have a poor ability to adapt things in an engineering-like sense to patch particular errors or things like that. Another disadvantage, which has been worked on a lot recently is that there are frequently huge problems with these models in terms of the biased language that they produce, or their ability to produce hateful or harmful language towards various groups. That this is, I think, something that can be worked on by doing more careful training of these models. But certainly up until now, a lot of the direction has effectively been the more text that we can throw into these models, the better they'll work. And that's effectively led to people putting in huge amounts of text from the kind of online sources that have fairly dubious content. And so often that these models are picking up on all the worst of human linguistic expression rather than trying to provide models that maintain a higher moral standard.
Okay, so we have another question. This is from the channel of YouTube. Deepak Kumar, if one stack pre-trained English-Spanish transformers encoder with pre-trained Spanish-English transformer decoder, will it work as an English-English model or vice versa?
So yes, it would work as an English-English model. So, you know, would it work better? I doubt it. But I mean, though it's sort of actually something you could still experiment with. So there's something interesting here. I mean, like on the surface, it seems like distributional learning, predicting words in context, is a sort of useful pre-training task, but it seems like it's semantically quite weak. And it seems a good idea to say, well, we have other things like translation, and translation is a much better semantic test of maintaining meaning. So it seems like we might be able to do much better in pre-training if we could work with bilingual models like an English-Spanish model, and then doing the vice versa, that we'd build much better models. And then if we plug the two of them together, we could have an English-English model via the intermediate language of Spanish or vice versa, and this should work better. I mean, that's an appealing idea. And maybe at some point, someone will get it to work in a way that it actually improves results. At least up until now, people who've tried that haven't been able to get it to work as well as just working with these monolingual distributional learning models. And I'm not sure I can convincingly say why that is, but it's partly a question of scale. You can get way more monolingual data. And I think somehow beyond that, there's a bit more subtlety still of sort of dealing with things that are translated exactly and not translated exactly. And at any rate, it's an interesting thing to try. I think it hasn't yet actually been proven to work better than starting off with monolingual distributional learning.
Okay. Rafael Gallardo Garcia, great talk. What do you think about the new transformers without the self-attention block? Are they promising in this kind of task?
So, I mean, honestly, I'm not sure. I'll say probably. I mean, I certainly think, right. So in the last year, there have been a couple of new transformer models, which then explore other ways of building things without having these attention blocks that tend to all the other words, and are using some more limited way, perhaps like older convolutions, to get some information about their context. I mean, I think it's super interesting that people are exploring these other models, because, you know, there's a kind of a weird everyone moved to transformers effect, that partly because these models are, you know, large, slow to train, that and transformers seemed to work so well. There was just everybody used this same transformer block. And indeed, it did work very well. And it wasn't sort of trivial to beat it. You know, a number of people, including me and some students, tried some variations of transformers, and they didn't seem any better. But you know, from a science perspective, that's sort of weird because transformers have this very particular architecture with a bunch of things, including the transformer blocks, but also normalization layers, fully connected layers. And it's hard to imagine the first thing people came up with is the very best thing that they'll ever be. So I think it's great that people are now more actively exploring alternatives. And indeed, people have at least found alternatives without attention blocks that work pretty well. I think it's not yet the case that anyone has found anything that is clearly better, but I'm sure that investigation will continue over the next few years.
Thank you. Any Bayer, do you think these large language models could assist in finding structures in language that linguistics have not yet thought of?
The optimistic answer is yes. You know, I think that sort of, to be honest, has to be approached with a fair bit of caution because a lot of it depends on your assumptions and whether you think the model is right, etc., etc. But I actually do think there's something interesting there, right? There are many constructions in the languages of the world, and sort of even for any particular language, there are sort of the very core constructions of sentences with subjects and objects and nouns with adjectival modifiers, etc. But languages always have a huge number of sort of weird constructions that appear in different places. And in a lot of those places, you know, linguists have argued back and forth for decades as to what's the best way to analyze those constructions. So when you have things like free relatives or tough movements or something like that, people will argue back and forth as to, you know, the best way to analyze a free relative is to say it is a clause and that this noun phrase is moved up front here, versus, oh no, we should analyze it as a noun phrase and this is a modifying clause behind it. And I think it's minimally at least interesting now to say, well, given that these models are self-organizing with their own structure, what kind of structure do they give to free relatives? I mean, you know, I doubt it's the case that for any syntactician, they will be able to be presented with, well, Bert says the structure looks more like this, and that'll be the end of the argument for them. But I think it would actually be an interesting thing to look at.
Okay, thank you. So we have a couple minutes to question. So the next is Joseph Mervin. Hi, Prof. Manning. Thank you for your talk. What are your thoughts and opinion on Google's very recent paper called FNIT based on fast Fourier transforms? They claim that FNIT offers an excellent compromise between speed, memory, and BERT. Do you think this framework will replace BERT?
Oh gosh, I think Joseph might have me on that one because I haven't actually looked at that paper, so I'm not sure I can give any particularly contentful answer to that one, I'm afraid.
Okay. Ayman Jundi, a recommendation of continuous remote education in cutting-edge NLP.
Well, I mean, I can certainly advertise my own course there. Though I can also mention other things. Yeah. So the natural language processing with deep learning class that I teach at Stanford, CS224N. CS224N, the entirety of it is available on YouTube or on a Stanford online site. And, you know, many people have watched those lectures and got value from them. What's up there at the moment is the 2019 classes lectures, but pretty soon over the summer, actually, we're going to update it with the 2021 lectures, which have considerably more content on transformers and large pre-trained language models. As well as the free versions available there. There's also a class that's offered that's available to anyone of XCS 224N, which is run as a cohort-based class with community TAs, which you need to pay money for, but lots of people have gotten value from doing that as well. That's clearly not the only option. There are a number of other great classes that are available online. Another very good one is Graham Nerbig's class that he teaches at CMU.
Okay, so this is the last question from Hilaria Cruz. Any ideas as to how we can integrate some of these models to analyze it endangered language, given the dearth of corpus and the lack of economical resource and lack of influence this language have?
Yeah, so that's a very good question and one that I'm interested in myself. Yeah, I guess I should have mentioned that when we were talking about what are the disadvantages. There's another disadvantage, right? The reality is that, you know, even for the sort of BERT-sized models that people are building them on billions of words of text, and some of the more recent models are much bigger than that. And well, the truth is that if you need that kind of order of text, then you're down to about 10 languages in the world that you can find enough text as languages like Spanish, English, Chinese. So that's clearly just never going to be the case, even for medium-sized languages, let alone endangered languages. And so that for lots of endangered languages, if you can collect together something like 250,000 words from the language, that counts as a lot. And so that's difficult. So, I mean, one answer is it sort of seems we'll just never be able to have the same kind of BERT models. And we need to work out ways of having things work well with less data. I mean, I think that that's a really interesting research angle anyway. I don't have the answers as to how to do that fully, but it seems like we need to sort of trade simply having scale for having more ability to sort of learn and generalize from the data that we do see. But, you know, in some sense, the comparison is human beings, that, you know, for human beings learning language as kids, you know, the estimates vary, but it's perhaps somewhere in the range of sort of 50 to 200 million words of data that they see, you know, a fair bit, definitely not billions. And one angle that is perhaps hopeful is there actually has been quite a bit of success at building multilingual BERT models or multilingual Roberta models. So not in all cases, but in quite a lot of cases, there are families of similar languages. And I think one of the ways that we'll be able to get better models from small amounts of data is by training multilingual models for families of related languages. So for something like Mayan languages, that seems like it might be a good strategy.
Thank you, Dr. Chris. So we close this talk. It was thoughtful and interesting. So thank you, everybody. And we say that we move to the different space to discussion panels. So Chris, you are invited in the table 2. So thank you, and we finish.
Thank you.